So we will officially begin. Welcome back. I hope everyone survived the storm last week okay. If you're here, that's probably a pretty good sign. So I hope we get most people logged on, so I'll know that everyone is still around and going to be able to participate. I hope you didn't have too many challenges last week. I was okay. I lost power for a little while, like everyone else did, and water for a little while, but no major catastrophes on my part. Of course, we lost a week, so that's going to throw us off a little bit, and we'll see how well we can catch up. I'm not going to try to kill ourselves trying to catch up that rapidly. Because it is calculus and we do want to take our time and enjoy the experience. I did postpone the test, though, obviously, which was going to be this Thursday, but I put that back until a week, until March the 4th. So we're just like a week behind schedule on the testing. These homeworks, I moved back a little bit. So we are talking today about, so these homeworks that I'm pointing to now, in WebAssign. This homework on measuring change, we've already started talking about that, and we're going to continue talking about that today. And so hopefully you'll be able to finish that homework assignment by Thursday. So it's not due today. I still have the due date set for Thursday. And then also today we'll talk about instantaneous rates of change, I hope, and we should. And then we've got that homework coming up, and that's set for Tuesday, but we'll see how well we're doing on that one. But we should be able to finish that one, I think, by Tuesday. Oh, well, let's see. We're up to 20 participants, so this is good. So we've got a good bunch still participating. I'm going to have to talk quite a bit today, so I won't get to interact with you as much as I would like to, but so that we can sort of make sure that we're moving through the notes at a pretty fast clip before the test, which is again a week from Thursday. Of course, the sample test is still there. We talked about that a couple of times before the break. If you let's see, don't forget now, if you are if we're not going to get many chances here to go over homeworks as much in class, because I'm sort of talking about the notes a lot, keep in mind, right, that you've got your sessions with Madison, right, that are available, so you can ask questions there. And then also you can book an appointment in the Math Center. Here's the link to the Math Center. So if you look at the announcements on the right-hand side of the WebAssign page, right, there's the link to the Math Center where you can make appointments for online tutoring. And so you can ask questions there as well. And those tutors, the ones that can tutor for calculus, they'll be easily able to answer questions, I think, about the homework. So don't forget about those options if we don't get a lot of time for going over homework problems in class as we're trying to catch up. Okay. But now, having said that, do you have any immediate questions? Anybody have any immediate questions that you want to ask me? It can be about the homework or about other things about the class. If you need something, if you need to ask me something right now. Any questions so far? Okay, and don't forget my office hours. I've been threatening to change those, but I haven't changed them yet, so they're immediately after class. So I'll be around immediately after class, and you can ask me questions there too during office hours, right? Also, don't forget the Ask Your Instructor link in our Ask Your Teacher. Not sure, it's either instructor or teacher with the questions, right? You can click on that button with a question, and it will email me the question, a copy of the question, and then I can see, what answer you had put, and I can see what the right answer is. So that's another way for me to offer help on homework problems. Okay, so don't forget about that option as well. Okay, so I'm going to dive right into where we left off in the notes last time, so we can make as much progress as possible today. And so let me switch to, let me find the right notes, just where we quit last time. And I'm going to change the share just to the, let me change the share just to the note pages. See, I think that's the right one. All right, so let me get to that. Okay, so so I assume you're looking at this this example 3, and we were last time discussing the different ways that we measure change. When I say measure change, I mean change in outputs from a function, right, as the input changes. Okay, so you know, functions in general, when you're looking at their graphs tend to wiggle a lot, right? They tend to increase and decrease, right? And sometimes they increase very rapidly, and sometimes they decrease very rapidly, or sometimes they increase slowly, or sometimes they decrease slowly. And so one of the things that we study in calculus is the speed at which outputs, y values from a function are increasing or decreasing, all right, as the x values are changing, as the x values are increasing, actually. All right, and so we talked about 3 measures, 3 basic measures of measuring the change in outputs for a function. One of them was net change, and then the second one, and this is mentioned in your homework, and then percent change. Not sure how many homework problems mention percent change, but percent change is important in practice in the real world, less so in calculus. And then also the one that we're really going to focus on, which is called average rate of change. All right, and we had just done some computations with average rate of change in the notes right before we stopped last time. And you're very familiar with average rate of change because average rate of change is essentially slope. The formula for average rate of change is really just the slope formula, except we're going to apply the slope formula to functions other than straight lines. Okay, so normally when we think of slope, we think of straight lines, but we can use that same slope formula and apply that to functions in general. And when we apply it to functions in general, the number that we get from that formula is not called the slope, but we can call it the slope, but it's more formally called average rate of change. Okay, let's just review this. We did this average rate of change computation last time, so you've probably forgotten about this calculation because this is the last thing that we did in the notes. But just as a reminder of how average rate of change works, so we were given this function 2x squared plus 3x minus 1. I didn't have any context to how this function was being used in practice. We just had this function formula. And so that's a pretty typical function formula, right? And we were asked to compute what was the average rate of change of this function from x equals 0, I'm sorry, from x equal 1 to x equals 3. So when we say average rate of change, we mean what's the average rate of change in the y values, the output values from this formula, as the input values, the x values, increase from 1 to 3. Okay. All right. So this is really an easy calculation, really an easy computation. I'm going to move my screen now, so you probably won't be seeing me, or you'll be staring at the top of my head or something. But it's an easy computation. Here's, by the way we symbolically denote average rate of change. We use this Greek letter delta, right, with either y or the name of the function. In this case, it's f. So this is delta f divided by delta x, right? And remember, this delta f means the net change, okay? So that's one of our measures of change. And that the net change is, a computation of the net change is involved in the calculation of average rate of change. And then this delta x in the denominator, this means the change in x. In this case, the change in x as we move from x equal 1 to x equal 3. So here's the here's the average rate of change formula. It's just f of your second x value minus f of your first x value. So this would be f of 3 minus f of 1. Our second x value was 3, right? Our first x value was 1. So we have f of 3 minus f of 1. So of course, we're going to have to calculate those using our function formula, right? Okay. And then divided by the change in x. Well, that's easy to compute. That's just x2 minus x1, or in other words, just 3 minus 1. Last time we calculated f of 3 using our formula, it turned out to be 26. There's the calculations up here. And we also calculated f of 1. That turned out to be 4. I think I made a mistake in those calculations at some point. But anyway, that turned out to be 4. And so we have 26 minus 4, right, divided by 3 minus 1. So that's 22 over 2, which is 11. So there's the actual answer to this question. The average rate of change from x equal 1 to x equal 3 is 11. Okay. Now, if you sort of picture here what we mean when we're calculating the average rate of change, here's in essence what we're doing. Okay. Look, here's a graph of this function, 2x squared plus 3x minus 1. Here's a graph of that over on the right-hand side, okay? So it's this red curve. You're gonna have to squint to see this because I just fit it in here on the page, so it's really small. But 2x squared plus 3x minus 1 is this red curve, okay? And what we've done, though, is from x equal 1 to x equal 3, we're going to sort of treat this curve like a straight line, all right? So what I've done is I've drawn a straight line here that matches the point that corresponds to 1 on the curve. That's 1 comma 4, by the way, because we calculated that f of 1 was equal to 4. And then here's the point that corresponds to x equal 3 on the curve. That, of course, was 26, because we had already calculated that f of 3 was 26. So this y value up here at this point is 26. And then I just drew a straight line connecting these 2 points, okay? And this number 11 that we computed, that's just the slope of this straight line, okay, that connects these 2 points on the curve. So, of course, the curve really isn't a straight line, right? From x equal 1 to x equal 3, it's got some concavity to it, right? In fact, it's concave up, right? This curve is concave up. But for the purposes of computing the average rate of change, we're going to treat the curve as though it were a straight line, okay? In fact, this straight line that connects these 2 points. This line has a name. I'm going to mention this again maybe today or maybe next time, but I've said this before already. This line that's connecting these 2 points on the curve, this is called the secant line, all right? So when you have curves that are not straight lines, and you connect 2 points on the curve with a straight line. So in other words, you sort of make the curve into a straight line between 2 points on the curve. That line that you create is called a secant line, all right? So the 11 is just the slope of this secant line. Now, what does that 11 mean to us? How does that help us measure change? What that means is the following. So here's our interpretation of average rate of change. I'm not going to write this down, so listen to me carefully, but we've written it down before. We'll write it down again. Just in this instance, I'm not going to write it down, okay? So what we would say is on average, from x equal 1 to x equal 3, the outputs or the y values from this function are increasing by 11, right? They're changing by 11, but 11 is a positive number, so the y values are increasing by 11 when x increases by 1, right? When x increases by 1. See, an average rate of change is a slope, so you're going to interpret it like we did slope, right? Okay, so the y values are increasing by 11 when the x values increase by 1. But it's important to point out that happens from x equal 1 to x equals 3, okay? This average rate of change only applies to this interval of x inputs, okay? See, that's different from a line, because for a line, slope is constant. So slope is always the same between any 2 x values for a line. So when you're interpreting the slope of a line, you don't have to say from x equal some initial value to x equal some terminal value. You can just say for a line, oh, this is how the y values are changing, right, as x increases by 1. But for a curve that is not a straight line, when you're interpreting average rate of change, you have to be more careful. You have to say, okay, from this initial x value to this terminal x value, from this first x value to this second x value, the y is increasing by some amount, or changing by some amount, could be decreasing, changing by some amount as x increases by 1 unit, okay? All right, well, you're going to do lots of average rate of change calculations in this homework that's due Thursday. So you'll get to practice this. This formula, which is just the slope formula, so it's very easy, right? You'll get to practice it a lot. Now, however, before we even are comfortable with average rate of change, I'm going to make it a little bit more complicated, all right? Because we're going to introduce some variables into our average rate of change calculation. All right, so for this same curve, okay, let's see if we can answer this question. I want to compute the average rate of change from x equals 2, all right, to x equal 2 plus some number. All right, there's x equal 2 right there. Okay, so we're starting our average rate of change at a calculation at 2. That's easy enough. All right, but now my second x value is not going to be a specific number. It's just going to be 2 plus some variable value. By the way, this number h, we're going to use this a lot, and I'm going to call this increment. All right, so we're going to yeah, I'm not going to be able to read my writing there, but that's the word increment. So we're going to compute the average rate of change starting at 2 and then going over to 2 plus some variable increment. So that could be 2 plus 1, or that could be 2 plus 2, or that could be 2 plus 3, right? Okay, we're going to leave this little extra value that we're adding on to 2. We're going to leave that as a variable, all right? But I'm just going to still go through the average rate of change calculations, all right? Even though that increment is a variable. All right, so now this is where, let me see if I can scroll up here. This is where I want you to watch carefully, because I don't want you to get boggled by this calculation, because it does involve a little bit of algebra, but it's not difficult. All right, it's just the average rate of change formula. All right, applied to this initial x value and this terminal x value. So remember, our notation for average rate of change is delta f divided by delta x, or it could be delta y divided by delta x, or it could be a different function name. So it could be delta g divided by delta x. And remember, that basic formula is f of your second x value minus f of your first x value, right, divided by the change in your x value. So that would be x2 minus x1, okay? All right, now, however, our x2 and our x1 in this case are what? Well, the x1 is going to be 2, all right? See, that's our initial x value. So that's easy. We're just going to plug that in for x1 in our formula. It's the x2 value that's a little bit different, right? Because our second x value is 2 plus some increment, all right? So that could be 2 plus 1, 2 plus 2, 2 plus 3, right? Okay, whatever value here we choose for h. Of course, that's going to be a number a little bit bigger than 2, right? Because you're adding something onto 2. So you'll get a value here that's a little bit to the right of 2, okay? So that's fine. And so this is the value that we're going to plug in for x2 in our formula, right? So we have f of 2 plus h minus f of 2 over x plus h minus 2. I'm sorry, 2 plus h minus 2, right? Okay, see, x2 was 2 plus h, so I plugged in 2 plus h for x2, and x1 was 2, so I plugged in 2 there, right? And then in the bottom, x2 was 2 plus h minus 2. Okay, so All right, so the bottom calculation is very easy, right? Because you have 2 plus h minus 2, so the 2's cancel, so you're going to end up here with h in the denominator. All right, so that's the easy part. It's the top part that's a little bit hard, right? Because we have to use our function formula. Let's see if we can remember I can't even remember what the function formula was. What was it there? Let's see, 2x squared plus 3x minus 1. Let me write that down here so I can remember it. So f of x was 2x squared plus 3x minus 1. All right, so first I have to take 2 plus h and plug it into my function formula. Yuck. So I'm going to get 2 plus h, I'm sorry, 2 times 2 plus h squared plus 3 times 2 plus h and then minus 1, right? See that? Because you're going to plug 2 plus h in for x in your function formula. So see, we have to do a little bit of algebra here to simplify all of these calculations. Now we're subtracting off f of 2. That's a little bit easier because we're just plugging a number in instead of this h, right, into the function formula. However, I want to caution you, let's put that computation for f of 2, let's put that in parentheses. It's very tempting to not do that, and that often leads to sign mistakes. So in parentheses, I'm going to write 2 times the 2 squared, right? So I'm going to write 2 times 2 squared, because this is 2x squared, plus 3 times 2, right? And then minus 1. And notice you're subtracting all of this in parentheses, right? Because in your formula, you have minus f of 2. See, all of this is f of 2. All of this in parentheses is f of 2, and we're subtracting that, okay? That's just part of the average rate of change. That's just part of the average rate of change formula. All right, oops, I don't have much room. Let me see if I can do all of this. I can do all this algebra in the space that I have. Okay, so first I have to take 2 plus h and square it. Now, this is another place where students are going to want to make mistakes when you're squaring 2 plus h, okay? Remember, when you square 2 plus h, that means you're multiplying it by itself. So let me write it up here. 2 plus h squared means 2 plus h times 2 plus h, right? And then when you multiply 2 plus h times 2 plus h, you get 2 times 2 is 4. 2 times h is 2h. H times 2 is 2h again. And then h times h is h squared. So be careful when you're squaring the 2 plus h. And don't forget, all of this is multiplied by 2, right? Still. Let's see. So what is that going to look like? We have 2 times, and then 2 plus h squared is all of this. So that's 4 plus 2h will add together. So you can combine those terms and get 4h, and then you have h squared, right? Okay, that's really the hard part. Once you've got that down, you're really in pretty good shape. 3 times 2 plus h is much easier, right? Just take 3 times 2 is 6. And then 3 times h is 3h, right? By the way, if I make an algebra mistake, y'all have to stop me. So someone's got to speak up very clearly because, you know, you can make algebra mistakes in these calculations. I can too, right? All right, and then the minus 1 here. Minus, and now let's see what's in the parentheses here. This is a little bit easier because this is just arithmetic. So you have 2 times 2 squared. I think that's 8. And then plus 3 times 2 is 6, and then we have the minus 1. And don't forget, all of this is still divided by this lonely h, which is in the denominator here. All right, let's keep simplifying. I think I have maybe just enough room. So now let's multiply in the 2 here. So I have 2 times 4 is 8, right? 2 times 4h is 8h. 2 times h squared is 2h squared plus, let's see, 6 plus 3h, right, minus 1 minus, what's all this in parentheses here? 8 plus 6 is 14, minus 1 is 13, right? All of this divided by h. Now let's see what we can add together. We have some like terms in our numerator here, don't we? Right? Okay, let's see. So we have some constants. We have 8 plus 6 is 14. I'm adding this 8 to this 6. So 8 plus 6 is 14. Minus 1 is 13. Minus another 13. Oh, yay. All of the constants have disappeared. So that's nice. Okay. So no constants. Let's see, what else do I have here? I have an 8h and a 2h squared, and then here's a 3h, right? So 8h plus 3h, that's 11h. And then I still have the 2h squared here. And don't forget, all of this is divided by h. Now we're in really great shape, because notice h will divide into both of the terms in the numerator, right? H goes into h and h goes into h squared. So you end up here with 11h divided by h. That's just 11. So you can get rid of that. And then 2h squared divided by h, well, I think that's just 2h, right? Because one of the h's will divide out. So there it is. See, that doesn't simplify all that badly. You just end up with 11 plus 2h, okay? All right, now, okay, you're going to wonder, what is the point of doing such an average rate of change calculation with a variable? And well, that's going to turn out to be a really important aspect in calculus here. All right, so don't worry. We're going to make use of that h. We're going to make use of that increment. That's really going to be vital to us. All right, now I can make it even harder here. All right, so that's exactly what I'm going to do, of course. All right, so now we want to find the average rate of change, same function, so I'm not changing the function. Here's the function, right? 2x squared plus 3x minus 1. Now I want to find from not a specific number like 2, but just from any value x over to that same x plus an increment, okay? So I'm just getting more and more abstract here. Here I was finding the average rate of change from a specific x value 2 to 2 plus some increment. Now I want to find the average rate of change from any x value. It could be 2 or it could be 3 or it could be anything, right? 7, all right? To that same x value plus an increment. So I want to go through the average rate of change calculations. I want to go through the average rate of change calculations very abstractly here. Starting at, this will be my x1. So my x1 will just be x. And this x plus h will be my x2. Okay. All right. Now I'm going to start the calculations for you, but at some point I'm going to stop here and let you guys finish. All right. So again, pay attention, because I'm going to stop and let you finish the work. So remember, this is the way we denote average rate of change, right? Delta over delta, right? And so I have f of x2, which in this case is x plus h, minus f of x1, which in this case is x, all of that divided by the second x value, which is x plus h, minus the first x value, which is, in this case, x. See how the denominator is going to work out so nicely now? Notice it's going to turn out again to be h, okay? So the denominator is very easy. What's tricky, right, is going to be this numerator, right? That's where all the work is going to be involved. Okay, whoops. Let me get back to my calculation here. All right. So okay, so let's try this, and so I'm going to try to start this now. All right, so f of x plus h. All right, so this means I'm going to take x plus h and plug it into my function formula. Remember, there was the function formula. So I'm going to plug x plus h in for x, right? Okay, so, So that sounds ugly, but let's see if we can do it. So that's going to be 2 times x plus h squared. Because remember, the first part of my function formula was 2x squared, but I'm plugging x plus h in for x, plus 3 times x plus h, and then minus 1. So all of this is f of x plus h. And now we subtract off f of x. Remember, you want to put that in parentheses, right? But f of x is just, keep in mind, f of x, this is just f of x. F of x is just the function formula. So you just have to plug in here the function formula, which is, I wrote it down wrong. It's 2x squared plus 3x minus 1. And then all of this divided by h. Okay, so that's a 2, right? Did I write that down right? Yeah, that's a 2. Okay. All right. So all right. So this is where I'm going to let y'all do a little bit of work here. Okay, because I want to see if y'all can do the algebra. Just see if you can simplify the numerator for me. Okay. So can you carry out all of this algebra and simplify for me the numerator? Just the numerator. The denominator is h, right? So we'll leave that alone. Well, there's no way to simplify h. It's simplified, right? But can you take the x plus h and square it, multiply it by the 2, multiply the 3 times the x plus h. Don't forget you have this minus 1. Then you have to subtract off. Remember, this is 2. Then you have to subtract off 2x squared plus 3x minus 1. You're going to have some like terms. Those can all add. Those will all add together. So when you've done all of this algebra and added like terms, what do you end up with here in the numerator? Okay, that's what I want to see if you can calculate. Can y'all calculate that for me? Okay, so try that. I'm going to give you 2 or 3 minutes, and then we'll see where we're at. Okay, so of particular importance is how do you square x plus h? Remember, x plus h squared means you multiply it by itself. So be careful about multiplying x plus h times x plus h. And then don't forget you have to multiply it by a 2. All right, so y'all working on that? Yes, no, maybe? Yes? Got to tell me something. Yes? Yeah, okay.
Yes.
All right. All right, so so be working on that. And then I'm going to ask someone to tell me what you got. And if you didn't get very far, that's fine. The class will help you. Okay, let's take a couple more minutes. It's fine if you're not completely finished. I just need to get your feet wet in doing these sorts of algebraic computations, because they're going to come up in the homework, and then they will, of course, surely be on the test, right? Because they're on the sample test. Okay, Damien, since you answered me early, just a second ago there, and I'm going to ask you to help us here with this. Ask you to help us with this numerator. All right, can you hear me?
Yeah.
All right. So let's just piece it together here. So when you multiplied x plus h times x plus h, can you tell me what you got from that? Just x plus h squared, just this part, without multiplying in the 2. Do you have that?
I put down 2x squared. X plus h.
No, before you multiply in the 2.
Okay.
So
yeah, x times.
Go ahead.
X times x.
Yeah, which is what?
2x.
Yeah, x times x plus x is 2.
Or x squared.
X squared, right? Yeah. So you have x squared, and then what else here when you're multiplying these two things? So you have x times x. You did that, right?
Yeah.
And then when you're multiplying these, what else do you multiply? You multiply x times h. So what would that be?
xh.
Yeah, I'm going to write it in, you can write it as xh. I'm going to write it.
Okay. Yeah.
I'm going to write it in alphabetical order. There's a reason for that. So you have x times h, and then you have that again, Damien. So you have h times x again, right?
Yep.
And then h times h, of course, what's that?
H squared.
H squared, right? Okay. So when you multiply x plus h times x plus h, this is what you get. These two terms you can add together, though, because they're like terms. So you end up with x squared plus 2 of these, 2hx plus h squared, okay? In parentheses, because you still have to multiply by this 2. All right. Now let's keep going, Damien. Before we multiply by the 2, what about 3 times x plus h? What would that give us? This part.
Times.
Go ahead.
3 times x.
3 times x. And then also what?
And I went over. Hold up.
Yeah.
I would think 3h or plus.
Yeah, 3h. And then just hanging around here by itself is the -1 for a moment. Okay. Yeah. All right. So let's just write that down. Now we have to subtract off in the parentheses. We have 2x squared plus 3x minus 1. But you're subtracting that. So the signs are going to change, Damien. So what would we have written down here?
X times X,
I'm-
or
No, I'm just
minus.
subtracting off
Oh,
these things. So when you distribute this minus sign, what would we write down here?
minus.
Minus, right? Minus what?
2x squared.
Right?
Isn't that a 3x?
No, no, this is a 2. I wrote 3 first, and then I changed it to 2. So that's really supposed to be a 2. So
Minus.
I may have messed you up with that. So minus 2x squared, and then what else, Damien?
Minus.
Minus what?
3x.
Uh-huh. And then
minus 1.
Be careful. This is minus minus 1. What?
Oh, I put minus 1.
Yeah, but it's going to really be plus 1.
Oh, 1 plus 1. Okay.
Because
yeah.
minus 1 is plus 1.
Oh,
Now-
yeah.
Yeah. Now, all right. So now let's multiply through this 2. Okay? Because I've got to multiply the 2 into the parentheses. So what would that give me, Damien? That just multiply 2 in there. So you get what?
4.
What's 2 times x squared?
2 times x. Oh, man.
That's just 2x squared. And then now 2 times this is what?
4.
Yeah, there's the 4. So you get 4h
Plus 4.
and then 2 times h squared. So that's just 2 h squared.
Yeah, 2h squared.
Yeah, plus, and then we have all of this stuff hanging around. So plus 3x plus 3h minus 1. This gets a little bit tedious sometimes to write these things down. Minus 2x squared minus 3x plus 1. Now, Damien, let's see if we can add like terms together, because we have, you can see them, I've written them so scribbly, but we do have some like terms. What about x squared? There's a positive 2x squared, right?
Yeah.
But then over here, we're so
There's a
lucky,
negative.
there's a negative. So those are going to disappear. And let's see, what else is going to disappear here? There's a plus
3x.
but there's a minus 3x. So that goes, there's a minus 1, and there's a plus 1. See, look, everything is kind of falling apart, right? So you end up with this, just this term, 4hx. Oops, I wrote it wrong. 4hx plus 2h squared. And then this. That one's kind of hiding in there, but 3h. All of this divided by h.
Oh, okay.
Ah, great. Now, we're almost done, Damien, because look what's going to happen. You just have h in the denominator, but that divides into all of these terms in the top. See, you can divide this h into this one. You can divide this h into this one. And it's going to cancel one of those h's because that's h squared. And then you can divide this h into this one. And this h will go away. So you end up with altogether 4x. See, 4hx, but the h divides out. So you get 4x, 2h squared, but you divide it by h. So you have just 2h left because the square goes away. And then 3h divided by h. Well, the h divides out and you end up with just 3. There's your, for what it's worth, kind of a strange final answer, but there it is. There's the final result there. Okay. That's what we're looking for. So it's a very abstract result. It's not a numerical result. It has variables in it, but that's the answer that we want. Okay. So if you got to that point, or if you got your numerator simplified right, and then you were easily able to divide out the h, then that's good. Okay, that means you're doing it right. You're going to be doing well on the homework. Okay, this calculation, by the way, where you're finding an average rate of change from x to x plus h, like we're doing here, x to x plus h. This is called the difference quotient. So what we calculated here was a difference quotient, but that's just a particular type of average rate of change. That's the average rate of change for some function from x to x plus h. Okay. Now there's a strange reason in calculus why this particular average rate of change is so important to us, or why difference quotients are so important to us. It'll take us a little while to understand what the importance of that. Okay. All right. Okay. So let's stop there. We're actually through talking about average rates of change. So we're going to take a little bit of a break here, so you can catch your breath and maybe repair your calculations if you if you didn't end up with this particular answer. All right. And then we're going to start the next notes, where we're going to look at a fourth measure of change called instantaneous rate of change. All right. But it'd take me a little while to explain the difference between average rate of change and instantaneous rate of change. Okay, so that's going to be the next notes. All right, so let me pause the recording and then we'll come back at 12:25. Okay. Okay, I'm back. So let's resume. I've switched the notes to the next set of notes. All right. So how did y'all do on those calculations in that previous example? Did you get very far into that, or did you make algebra mistakes, or just got lost, or how was that? Anybody want to volunteer? How they did?
For me, it was okay. It wasn't too bad.
It wasn't too bad. Is that what you're saying?
Yeah.
Oh, okay. All right. Anyone else there? Easy, hard? Oh, okay. So, all right. So Angel says she sees where she went wrong, at least. Okay, so that's good. All right. Because when you find and correct your mistakes, then that's how you learn. All right. Okay, so again, there's plenty of those examples in the homework that's due on Thursday. So actually, we're through talking about that, or at least going over examples for that homework on Thursday. Okay, these notes are going to pertain to the next homework, which I have due the following week. I'm going to start off now with a very, very easy example, because I'm trying to get you to sort of understand conceptually this idea of instantaneous rate of change. All right. So again, we've got these, we're now up to, or we're going to, as soon as we talk about instantaneous rate of change, we'll have four ways of measuring change, right? We have net change and then percent change. Those are kind of elementary. And then we have average rate of change, and a little bit more difficult. And then a lot more sophisticated is going to be this notion of instantaneous rate of change. All right. But I'm going to start off with just a trivial example, and just so that we can work slowly into this notion of instantaneous rate of change before it gets a lot more challenging to us. All right. So here's the example. You can read it off the screen there. It says Freddie is leaving for a weekend trip on his scooter from campus on Friday after classes end. And this line that's graphed here, this function just relates his distance from his house, not from the campus, but his distance from his house after X hours. All right, this is distance in miles. Okay, so Y is distance in miles and X is elapsed time in hours after he leaves the campus. All right, so very easy graph to read, right? Okay, so apparently initially, right, at time zero here, Freddie was, let me get my pen to work. Initially at time zero here, it looks like Freddie was 10 miles, roughly, right, away from his house. And then after 1 mile, after 1 hour, he was, 30. And then after 2 hours, he was 50 miles away. And then after 3 hours, he's 70, and so on and so forth. Okay. All right. So the graph of Freddie's distance away from his house is very simple, right? It's just a straight line. So not a complicated situation here at all, right? Okay, now let's look at the questions though. So first question is, and again, these are going to be very, very elementary questions, right? Because it's a very simple example. It's just, what is the average rate of change? What's the average rate of change of Freddie's distance, right? The average rate of change from x equals 0 to x equals 3. So this would be from the time Freddie leaves, right, to 3 hours, right? What's the average rate of change in y, his distance in miles, right? Okay. All right. So so you don't really have to think about, you know, too much about what's being asked of you here, right? You can just grind through the calculations, right? So we would have delta, I'm going to call it y over delta x, right? And so that's just, remember, that's going to be y2 minus y1 over x2 minus x1, x2 minus x1. The x2 here is 3, right? And the x1 is 0, right? Okay. And then y2, well, we can read that off of the graph, right? When x is 3, the y is 70. So y2 would be 70. And when x is 0, right, the y2 is, I'm sorry, the y is 10. So you would have 70 minus 10 over 3 minus 0. So that's easy. That's 60 over 3, which is 20. Okay. So you get that the average rate of change here is 20. Notice that all we were really doing again here is calculating slope, right? And in this case, since our function is a line, then this average rate of change is really just computing the slope of this line, right? Okay, so in this very simple example, this average rate of change is just the slope of the line, and that's very easy to compute, or you can almost read it immediately off the graph, right? The slope of this line is going to be 20. Okay. Now, if you want to interpret this this average rate of change, right? If we follow the the recipe that I have been emphasizing here, we would say on average, right, from x equals 0, right, to x equals 3, right? Okay. The distance, which is y, the distance increased, right? Because this number is positive. So we would say the difference increased by 20, right, miles. And that would be every time x increases by 1, well, when x increases by 1, that would be per hour, right? Because x is time measured in hours. So on average, right, from hour 0 to hour 3, Freddie's distance increased by 20 miles per hour. Okay. Now, look, for this simple function, since it's a straight line, notice that if I ask this same question, but for different x values, right? For different x values, the answer is going to come out the same. Okay. So if I ask, what's the average rate of change from x equals 3 to x equals 5? I mean, you can go through the calculations if you want to in the formula, but notice you're going to come out with 20 again. Okay. You're going to come out with the same value. There's really no reason to go through the calculations because this function is so simple, right? This function is a straight line. And when you calculate the average rate of change of a straight line, you're really just calculating its slope. And it doesn't matter if you're calculating the slope from x equals 0 to x equals 3, or from x equals 3 to x equals 5, for straight lines, remember the slope is steady, right? The slope is always the same. So, I mean, when you go through these calculations, you already know you're going to come out with 20, right? Okay. And the interpretation will be almost, the interpretation will be almost the same as before. You could say, you know, on average, from x equals 3 to x equals 5, right? The distance increased by 20 miles per hour, right? All right. So, you know, for straight lines, again, average rate of change really just the same as average rate of change, really just the same as slope. And in fact, for straight lines, you really don't even need to include this phrase on average, okay? So in your interpretation, you could have dropped the phrase on average because, again, the rate of change for lines is always steady. So this is not what's happening. I mean, this change is not what's happening on average, right? This change is you know what's always happening, correct? It's not just from x equal 3 to x equal 5, right? Okay, it's also the rate of change from x equal 0 to x equal 3, or from x equal any starting value to x equal any ending value. Okay. Now here's the thought question though that I want to ask, but it will be very easy to answer. Look, if Freddie is on his scooter and he is, of course, the scooter is going to have a pedometer on it, I mean, a speedometer on it, right? So supposing that after exactly 1 hour, Freddie looks down at his speedometer, right? That tells him his speed, obviously. What's Freddie going to see on the speedometer? So that's my question to the class. What's after 1 hour? So exactly after 1 hour, Freddie looks down to look at how fast he's going. What's Freddie going to see there on the speedometer? Just what does it have to be?
20 miles
20, right, yeah, Damien, sure, yeah. It's got to be 20, right? Okay. I mean, that's just how fast Damien's going, right? Okay. So he's going to be C20 mph, right? Damien, by the same token, after 4 hours, right, when he looks down at the speedometer, what's he going to see? So if he looks down after 4 hours, what?
No, hold on 1 second.
Same thing, Damien. Okay.
Oh,
Still
okay.
going to 20 miles per hour, right? Okay. Because Damien's rate of change, Freddie's rate of change, Damien, is steady, correct? You can see that from the graph, right? Okay. The fact that this graph is a straight line just means that his distance is increasing always at a steady rate, right? So from 0 hours to 3 hours, he went on average 20 miles per hour, right? From 3 hours to 5 hours, he went on average 20 miles per hour. If he looks at his speedometer after 1 hour, right, he's going to see 20 miles per hour, right? That's just how fast he was traveling, correct? Okay. So it's very easy to answer these two questions once you realize, right, that you're dealing with a linear function here, right, for Freddie's distance. All right. Now, however, let's look at a different situation. All right. So not Freddie on his scooter, but also a situation where we want to think about speed. Okay. All right. So here's the story. A construction worker is drops a screwdriver off of a building. Okay, so he accidentally drops a screwdriver off of the building. And of course, the screwdriver is going to drop straight down to the ground, right? Okay. We know a lot about falling objects, especially how fast they fall, especially objects that are not very aerodynamic, like screwdrivers. Okay. So the screwdrivers are not going to be influenced much by the wind. All right. And so really it's just gravity that's going to influence the how fast how fast that screwdriver drops. All right. So this function, which is very easy to derive, okay, will give the height of the screwdriver a given number of seconds after it was dropped. Okay. So and this is formulas like this one have been known for a long time to physicists since the time of Galileo, okay, who studied falling objects and the height of falling objects. All right, so we want to think about this particular situation. We've got a screwdriver that's dropping. So of course it's dropping at a particular rate, right? The screwdriver has a speed, okay? And that's what we want to think about. Just like Freddie's driving on his scooter at a particular speed, this screwdriver is dropping to the ground at a particular speed, right? Now, let's start off with a very easy question, though. This is just an algebra question. I want you to evaluate for me f of 0 and tell me what that means. Okay, so compute for me f of 0. That will be easy. And then tell me what is f of 0 in the context of the problem. What does f of 0 mean? All right, so what's f of 0 telling you when you calculate that value from the formula? So do that for me, and then I'm just going to ask someone to tell me. Okay, so we don't need a lot of time to do this calculation. Let's see, Angel, you were answering earlier. Are you still there? Did you calculate f of 0? Angel Cardona, did you calculate f of 0? What? That's just going to be a number. Are you there? Were you able to compute that? I think sometimes Angel loses her connection there. Angel Martinez instead of Angel Cardona. Can you tell me? Okay. All right, Angel. All right. I'll come back to you then because we still have some other problems. But Angel Martinez, are you there? Did you calculate f of 0? Were you able to compute that? It's just a matter of plugging 0 into the formula. Oh, okay. So I got an answer from Damien, but Angel Martinez, is Angel Martinez there? He's showing on my participant list, but speak now, Angel. I'm going to mark you here.
Did you want just to add 0 to the equation?
Yeah, just compute f of 0. That just means you're plugging 0 into the formula, right? That's all.
Well, then you just get still 400 because minus 16 times 0, it's going to be 0. So it's just 400.
Yeah, that's right. Yasan, that's correct, right? F of 0 is going to be just 400, right? Because when you plug 0 into this formula for x, the second term will just disappear, right? And so you just end up with 400. Yasan, what does that mean, though? In the context of the problem, what is that really telling us? So what is that 400?
So with the equation on the problem, it would just mean so that's how many feet.
Yeah, the 400 is feet, right? So there's 400 feet, but you have to get the x equals 0 in there. So it's 400 feet. How would you work the x equals 0 into your interpretation?
The building is 400 feet tall.
Yeah, Van, that's correct, right? Because it's going to be 400 feet when the seconds is 0. Well, when the seconds is 0, that means right when the construction worker releases the screwdriver, right? Okay, right? When time is 0, that's when the construction worker initially releases it. So, in other words, the initial height of the screwdriver, right, when it's dropped is 400 feet, or as Van said, the height of the building is 400 feet, right? Okay, so that's all we're learning from when we calculate f of 0. The initial height, right, of the screwdriver is 400 feet. So it's going to drop 400 feet before it hits the ground below. Okay. All right. Well, now we can quickly answer then the second one. It says evaluate f of 3, right? Well, that's pretty easy to do, right? F of 3 is just going to be 400 minus 16 times 3 squared, right? So we just have a little bit of arithmetic to do here. So we have 400 minus 16 times 9. How much is 16 times 9? 144. So we have 400 minus 144, which is 256. All right. Or if you want to interpret that, you would say after 3 seconds, right? After 3 seconds, the screwdriver is at 256 feet, right? Or 256 feet off of the ground, something like that. So the height of the screwdriver is 256 feet after 3 seconds, right? Obviously, after 3 seconds, some time has gone by. The screwdriver is dropping, right? So it's dropped from its initial height, right, down to 256 feet. Now, since we did those two calculations, let's calculate the average rate of change from x equals 0 to x equal 3. All right, so let's do that average rate of change calculation. That should be easy to do, right? Because we've got most of the calculations, right, already done for us. Okay, so here's my notation for average rate of change, right? And we want from 0 to 3. So we would have f of 3 minus f of 0 over 3 minus 0. Okay. And so we just said f of 3 was what? 256, right? Minus f of 0 was 400. And we're dividing this by 3. So I end up with minus 144 divided by 3. And 144 divided by 3, or minus 144 divided by 3 is going to be something like 48. Is that right? Don't let me make a mistake there. All right, so I think that's it. Minus 48. Okay. What is that minus 48 now? If you're going to interpret that, how would you interpret that? So remember, this is an average rate of change. So how would we explain what that number means to us? Okay. Notice it's negative, by the way. So if on the test I say, okay, tell me what that number means in the context of the problem, interpret that number in the context of the problem, what would you say? Angel, can you
draw 48 per second feet per second?
Yeah, it's something to do with the speed of the screwdriver, right, Van? Okay. So let's see if we can say it correctly. We would say on average, you've got to start with the on average here, okay, from x equals 0 to x equals 3, from x equals 0 to x equals 3, the height of the screwdriver changes, or you can say the screwdriver falls. It's falling because this number is negative, right? So the screwdriver falls by what, 48, and what is it, feet per second, right? Because we're measuring the height in feet and the time in second. Does that make sense to everybody? Okay, so over the first 3 seconds from x equals 0 to x equals 3, the screwdriver is falling by 48 feet per second. Now look, in this case, this curve 400 minus 16x squared is not a straight line. So you are going to make a mistake if you take off the on average. If you take off the on average and you just say from x equals 0 to x equals 3, the screwdriver falls 48 feet per second. Why is that a mistake? Let me show you the picture why you have to have the on average in there. Here's actually the picture of this, the graph of this function. This is not the path of the screwdriver, by the way, because the screwdriver is falling straight down. Okay, so the screwdriver starts at 400 feet and drops straight down. Okay, but this is the graph of that function, 400 minus 16 x squared, right? Okay, and if you look at the graph of this function, right, see, this is the height and this is the time. You certainly do get an idea of what's happening to this screwdriver falling, right? Because as the time is going by, what's happening to this curve? It's getting steeper and steeper, right? So what does that tell me about the speed of the screwdriver?
The speed is increasing.
Yeah, right, sir. Sure, right, okay. The speed of the screwdriver is increasing, right? This curve is dropping more and more rapidly, right? Okay, as the time passes, correct? In other words, the screwdriver is falling more rapidly. So, Saad, you cannot say from 0 to 3 seconds, the screwdriver was falling at 48 feet per second, okay? Initially, the screwdriver wasn't falling very rapidly, right? Okay, but as you get over here toward 3 seconds, here's 3 seconds, there's that height of 256. As you get over here toward 3 seconds, then see the screwdriver is picking up speed, right? You know that. That's just gravity is accelerating the screwdriver, correct? Okay, so you cannot say the screwdriver was falling steadily at a rate of 48 feet per second. All right, that's what was happening on average, okay, from 0 to 3 seconds. At 3 seconds, it was going much faster than it was going when the construction worker initially let it go, right? Okay, Saad, if the screwdriver had been falling steadily at 48 feet per second, what would this graph look like?
It would be a straight line.
It would be a straight line. Perfect. Yeah. If the graph were, if the screwdriver had fallen at a steady rate, this would just be a straight, this graph would just be a straight line. So you would just connect these 2 points with a straight line, you see. Oh, by the way, Saad, what's the slope of that straight line that I just drew there? That's supposed to be a straight line, by the way. Okay.
Right, we did the
I
average
got a little
rate of
wind turbulence in there. What, Saad?
We had calculated the average rate of change.
As what? You remember? We just calculated what was that number? Angel, what's that? Angel Cardona, what's that number? You just told me. Oh yeah, there it is, minus 48, right, okay. We just calculated that, right? It's minus 48, right, okay. So had the screwdriver fallen at a steady rate, this graph would look like this, and the slope of that line would be minus 48. By the way, again, what's this line called? What's that line called that connects these 2 points on the curve? What type of line is that?
Secant line.
Yeah, that's a secant line, right? Okay, that's just a secant line. All right, now look, when we calculate in a second here, now we're going to calculate the average rate of change from 3 to 5. Okay, so we're going to calculate the slope of this secant line, the average rate of change from 3 to 5. And notice that, I really drew that one bad. All right, so notice that that line is steeper, right? Okay, that line is, this line, the second secant line is steeper than this first one. The secant line from 3 to 5 is steeper than the secant line from 0 to 3. Of course, why is this secant line steeper?
Because our function was squared.
Yeah, it's because the function is squared, Lance, but in the context of the problem, why does that, in the context of the story, why is that secant line steeper?
Oh, is it because like it's accelerating?
It's accelerating, right? The screwdriver is going to be dropping faster, right? Okay, the screwdriver is going to be dropping at a faster rate, okay, from 3 to 5. All right, so let's calculate that. All right, that's pretty easy. All right, so what's this average rate of change from x equal 3 to x equal 5? I'll let y'all calculate that. By the way, so we already computed f of 3 a moment ago, so you have that. Remember, f of 3 was, what was f of 3? 256. And here I calculated f of 5 for you. It turns out to be 0. Okay, so f of 5 turns out to be 0. So calculate for me the average rate of change. All the values you need are here, from x equal 3 to x equals 5. All right, just take a minute to do that. It won't take long because you have the numbers that you need there already. Okay, did y'all get that calculation? Don't want to rush you here, but so let's see. This average rate of change is going to be f of 5 minus f of 3 over 5 minus 3, right? What does that turn out to be? Someone minus 128, Saad, is that what it is? Did someone else get that?
Yes.
Yeah, I got that too.
All right. So minus 128, once you fill in the values for, yeah, that looks right. We can almost do that in our heads, right? So minus 128, right? So that tells us that from the 3rd second to the 5th second, right? On average, that's important though. On average, from x equal 3 to x equals 5, right? From x equal 3 to x equal 5. The screwdriver drops 128 feet per second. So dropping much more rapidly, right? Okay, from the 3rd second to the 5th second than it was from the initially, right? From second 0 to second, from second 0 to second 3. So, and that's easy to see, right? From the, very easy to see from the picture, right? So the slope of this line is minus 128. Okay, now here's the thought question though that I have for you, all right? So imagine that right here at 2, this is 2, I think that's 2. Right there at 2, I'm not sure what the height is at 2, but right there after 2 seconds, suppose this screwdriver had a speedometer on it, okay? And so just imagine that. So this is a thought experiment. So imagine that the screwdriver had a speedometer on it, and we were looking at that speedometer at exactly the instant 2 seconds, right? So exactly after 2 seconds, we looked at the speedometer on the screwdriver. What I want to know is, what would that speedometer say? Okay, so exactly after 2 seconds, how fast is that speedometer dropping? Right. So you see in Freddie, in the prior problem, in the Freddie example where he's on the motor scooter, because that function was a straight line, it was easy for us to deduce, right, that after 1 hour or after 4 hours, when Freddie looked at his speedometer, he saw 20 miles per hour. Okay. But here, it's a much trickier question, correct? Okay. Because the screwdriver is accelerating, right? Okay. So if we're able to look at it right there after 2 seconds, what would the speedometer read? Or here, let me ask the question slightly, same question, just in a slightly different place. When the speedometer hits the ground, by the way, it hits the ground at 5 seconds because f of 5 was 0. So when the speedometer hits the ground, exactly when it hits the ground, how fast is it dropping? So if you are standing underneath the screwdriver, I don't think you want to be, but if you're standing underneath the screwdriver, how fast is that screwdriver going to knock you in the head? Okay, so how fast is the screwdriver dropping exactly when it hits the ground? Okay, so that's the question that we want to that's the question now that we want to see if we can answer. All right, so the hard question, right? Okay, because doesn't seem like we have a whole lot to work with here, right? But now we're going to do this, but we're going to play this game like a mathematician, and we're going to think about this like a mathematician would think about this, okay? Which is essentially, we're going to cheat a little bit on the question, all right? Folks, class, if this curve, okay, so if this curve, I can get my pen to write. All right, so you already know this. If this curve had been, if we were lucky, and this curve had been a straight line, right? So if the curve had been a straight line from, from the beginning all the way here to when the screwdriver hits the ground, and if I ask you, how fast is the screwdriver dropping after 2 seconds, right there after 2 seconds? That would not be a difficult question to answer, right? How would you answer that? So if the screwdriver had fallen according to this straight line, and I ask, how fast was it going after 2 seconds? What would you say? Or how would you answer that? Not what is the answer, but how would you go about answering it?
You would just find the slope of the whole line.
Yeah, you would just find the slope of the line. Sure, right. Okay, this would be exactly like the problem before, right? This would be like Freddie's problem, right? I would just find the slope of this line, and then since the rate of change of lines is always steady, then it would make perfect sense to say, well, the rate of change of the screwdriver after 2 seconds is, whatever the slope of this line is, right? Okay, the screwdriver would always be falling at a steady rate, right? If this were a straight line, the screwdriver would always be falling at a steady rate. But so easy, right? I would just say the slope of whatever that slope turns out to be, that would be what would have to be on the speedometer at that instant, correct? Okay, at exactly 2 seconds. That would also, by the way, have to be what was on the speedometer after 3 seconds or 4 seconds, or when the speedometer, I'm sorry, that would have to be what was on the speedometer after 3 seconds or 4 seconds, or when the screwdriver hit the ground at 5 seconds, right? The speedometer would always give the same reading, okay? Of course, what messes things up here is that, as we've discussed, right? Unfortunately, this curve is not a straight line, right? We don't have a straight line here. Or do we? All right. Or do we? Okay. Here's what let's look at. So I'm going to switch back to, let me change the sharing here back to the screen. And I'm going to look at just the graph of this function, but I'm going to look at the graph of the function drawn in Desmos, where I can manipulate it a little bit. Okay.
What's the, really quickly before you do that,
Mhm.
sorry, what's the equation for that?
For that, for the screwdriver, it was for the line.
For that, the graph of the screwdriver question.
It was 400 minus 16 x squared.
Okay, thanks.
Yeah. By the way, any object under the influence of gravity, if you and this it would be a grain of sand or a bowling ball, right? Okay, if you're able to ignore wind resistance, you'll get that same formula. Donna, the first number is going to be the initial height, though, right? Okay. So if you drop something from an initial height, you put that, and then it's going to be minus 16 x squared, where x is the time in seconds, right? Okay, so there's nothing really unique about the screwdriver here. All right, so now let me, here's the graph now, though, here's the graph of that same graph that we were looking at, okay? And again, we're interested in, right here at x equals 2. All right, now look, here's what I'm going to do, though. Let's start blowing up this graph, right? So I'm going to start zooming in on this graph right around x equal 2. So right around this point. Let me make sure I can do this right now. Okay, so I'm going to have to move things around. So I'm zooming in right here at this point. See, there's x equal 2. Can y'all see that? Is that visible?
Yeah.
All right. So, and I'm going to just keep zooming in on this. So I've zoomed in quite a lot now. So there's 2 again on the x-axis. And I'm going to stop right there. I'm happy to stop right there because what does that graph look like?
Straight line.
Ah, it looks like a straight line. That's right. Okay. So notice that close here, very, very close, very, very close to x equal 2, the graph just looks like a straight line. Okay. So guess what? We can treat it very close to x equal 2. We can treat it as a straight line. All right. Because it looks very much like a straight line, right? Okay. That means then that for this piece of the curve, notice this only goes from 1.8 over to 2.2, right? So that's x equal 1.8 over to x equal 2.2. For that piece of the curve, we might as well assume that what we have here is a straight line, okay? That means then that for this little piece of time, from x equal 1.8 over to x equal 2.2, that little tiny fraction of time, essentially the screwdriver was dropping at a steady rate. Now, it wasn't completely dropping at a steady rate, okay? Because this curve is not a straight line, all right? You know that it's not, right? Because when you zoom out, you can see that it's not a straight line. But essentially, for this little brief window of time, essentially, the screwdriver was falling at a steady rate. So if we calculate the slope of this straight line that we're looking at, right, that means that all during this time period, this brief time period, the screwdriver was essentially falling at a steady rate. And then that would be the answer to what is on the speedometer after 2 seconds. Okay, so see what I did here? I just zoomed in on this curve. If I zoom in far enough, long enough, that curve we know is going to appear to be a straight line. Okay, therefore it's going to behave like a straight line, and straight lines have steady rates of change. Let's calculate now the slope of this, I'm going to say quote unquote straight line, because we really don't have a straight line here, right? To calculate the slope of this straight line, you're going to have to pick 2 points off of the line. So let me see if I can pick 2 points off of the line here. I'm going to start at, let's start at this point where x equals 1.95. Let me point at this and see if it will do a calculation for me in decimals. Y'all may have to write this down for me now. Oh, it's very friendly. Well, I missed, oh, no, oh gosh, can I move my, trying to get the, there we go. Write that down really fast. So when x equals 1.95, the height, the y value is 339.16. Did y'all write that down for me?
1.9.
So there's 1 point on this quote unquote straight line, which is really the curve, which is really not a straight line. But here it looks like a straight line because we've zoomed in so much. So write that down, 1.95 and then 339.16. Now let me shift over to a little bit to the right. So let me go to 2.0, see if I can get 2.0. Oh, there it is. So there's 2.05, and the y value there is 332.76. 332.76. Did y'all write that down?
Yeah.
So what we know is f of 1.95 is this first value over here, okay, whatever that was that y'all wrote down, and 339.16, and then f of 2.05 is this value. If I can find it again, there it is, 332.76. And let's do our average rate of change calculation with these numbers. All right, okay, so that's what I'm going to do. Let me switch back to the notes here. And let's do that quickly here. Let's do that average rate of change calculation. So delta F over delta X is going to be, let's see, what X values did I use there? 2.05 minus 1.95, right? Okay, those were the two X values that I used, close to 2. And then what were the two output values? What was this one? What was F of 2.05?
332.76.
332.76 minus, and then this one was, what was F of 1.95 there?
339.16.
339.16.
Mm-hmm.
All right, so can y'all do this arithmetic for me quickly? You have a calculator. This one's pretty easy on the bottom. That looks like 0.1, right?
Mm-hmm.
And
The top is negative 6.4.
minus 6.4.
Uh-huh.
Minus, no, it can't be 6.4.
Okay, wait.
Oh, no, you're right. I'm sorry. Minus 6.4. So we get, oh, this is nice. Minus 64. Wow. Nice value there. So essentially, in this time frame from 1.95 to 2.05, since this function looks like a straight line, right? It's essentially a straight line, right? You cannot really see the curvature here. That means that from this little time span, the screwdriver was falling at a steady rate, and that steady rate was minus 64 was 64 feet per second. So if you had looked at the speedometer at 2 seconds, you would have seen 64 feet per second. Okay, there's how we answered this question. This is now called, what we've just calculated is now called an instantaneous rate of change, because we're asking how fast is the screwdriver falling at a particular instant, not from one time to a second time, but from at one particular time. But notice we calculated that instantaneous rate of change by using an average rate of change. But an average rate of change for what sort of curve? What's the key? The curve must look like what?
A straight line.
The curve must look like a straight line. So if you have a curve that's not a straight line, you're going to have to zoom in on a piece of the curve that does look like a straight line to calculate an instantaneous rate of change. All right. Well, that wasn't too hard to do, actually, but notice we did need Desmos to help us with that, okay? So what we're really going to be focusing on here for a couple of lessons is calculating more instantaneous rates of change and understanding them better, but learning how to calculate them by hand without using Desmos, all right? So, Isaac Newton calculated instantaneous rates of change, but he didn't have Desmos. So how did Newton figure out how to do this, right, without having Desmos? Okay, all right, so we've run out of time. Oh, we're exactly right on time. So we're done for today. So remember, this homework now that's due Thursday, we've gone over the notes for that. So you should be able to work on that. And we'll continue talking about instantaneous rates of change next time. Okay, all right, so we did pretty good today. Excellent progress. Sorry I had to talk so much, but just had to do that. Okay, I'll see you guys on Thursday.
Thank you so much. Bye-bye.
Thank you.
Bye.
Bye, guys. See you Thursday.